It's my pleasure to introduce Professor Rajneesh Bhardwaj. He is currently the professor in the Department of Mechanical Engineering, IIT Bombay. He completed his B.Tech from NIT Surat, MS from Stony Brook University, PhD from Columbia University, New York, and later joined postdoc position at Johns Hopkins University, Baltimore. He was awarded with Columbia University distinction for outstanding doctoral thesis. He joined IIT Bombay in 2012 as assistant professor. He has been awarded with prestigious Young Engineer Award and Young Associate by Indian National Academy of Engineering, Young Engineer Award by Institutions of Engineers India, Sub-Star Award for year 2022, and many more. He has been included in the advisory board of high-quality peer-reviewed journals like Nature Scientific Reports and Experimental Thermal and Fluid Science. His area of research expertise are droplets and colloids and interfaces, fluid structure interaction, and immersion boundary methods. His dedication to advancing knowledge in his field is evident through his numerous publications in top-tier journals like Journal of Fluid Mechanics, Langmuir, Physical Review Fluids, Sadhana, Journal of Fluids and Structures, and International Journal of Heat and Mass Transfer. Today, we are privileged to have Professor Rajneesh Bhardwaj with us to share his insights and expertise on the topic fundamental of fluid structure interaction and vortex-induced vibrations. Please join me in extending a warm welcome to Professor Bhardwaj.
Okay, thank you, Dr. Somnath, for the nice introduction. And at the outset, I would like to thank Dr. Subhankar Sen to invite me for this workshop, and my apologies for not joining you offline. And a hybrid method is to do online so that you can actually get to see the work our group is doing. So thank you, Dr. Sen, and let me just start my talk today with computational modeling and some application to thermofluids problem. Okay, so roughly I'll take around 50 to 60 minutes, and if you have any question in between, feel free to ask. And I would like to have it be more interactive rather than just questions at the last. So the talk today is actually on the computational modeling. And before I go to that, let me just introduce some of the motivation or some of the application which we have. And even before that, I would like to acknowledge all the people who have contributed to the data I'm showing here in these slides. So these are mostly my former and present students. Dr. Atul Soti, he is on the faculty at IIT Guwahati. He was PhD student in our group. Dr. Hemanshul Garg, he is already graduated and postdoc in Denmark. Dr. Anup Kundu is faculty in SRM. And these are two present students, Gaurav Sharma and Avinash Pandey. Gaurav has almost submitted his thesis and going to join postdoc position as well. And Vedant was project staff who later joined higher studies. I also acknowledge discussions with Dr. Professor Rajat Mittal, who is at Johns Hopkins University, and funding for this work was provided mostly by DST. Now let us look at motivation. Why would be somebody interested in the modeling of FSI problems, and that too also involved heat transfer or thermofluids? So you actually see two columns in which I have put different pictures. One for the engineering systems and second for the biomedical or biological systems. So if you see here, this part is a chip cooling mechanism or fins on a chip where you can extract the high heat. And if you want to model this system, you have to model this complex shape, which is immersed in a fluid and which is releasing heat to the air or any method you are cooling. So it can take or extract the larger heat from the chip. So modeling of it requires this representation of these surfaces or this geometry accurately, and the knowledge of fluid flow and the heat transfer. Second example in engineering system is the piezoelectric fans, which have been used to cool any surface. So let us say this example is showing a heated sheet which is cooled by these piezoelectric fans. So when these fans are vibrating or deforming, they create secondary flows like vortices, which helps to cool this sheet. As you can see here, the thermal signal, this is being cooled at the center. And this third example is metal form. So you can see the larger picture here. This is the zoomed in view of this. So these are metal forms. You basically inject a bubbly flow in a molten pool of metals, and these surfaces or these materials such created are very efficient in removing the heat or transferring the heat, and they are also very lightweight as compared to the metals. This is an example of re-entry vehicle which is entering back into the Earth atmosphere, and it is exchanging heat in that atmosphere. In biological system, this is an infrared image of elephant, the body signal or the temperature body signal of the elephant, where it is shown that you can see the ear is at the low temperature, which means they use their large ears to cool themselves off or release the heat from their bodies. This is an infrared signal for the penguins. They are doing the same thing, but in a very cold environment. So their flippers are of use here. This is heat transfer from the leaf. So plants also thermoregulate themselves, and based on the wind speed and based on the temperature during the day or the time during the day, the heat transfer could be very different. So here the themes are the vibration of the leaves and the complex geometry which can be used to remove the heat from the leaves. And the fourth example in biological system is cryosurgery. So when cryosurgery is being planned, so somewhere deep into the tissue, you send out a cold fluid or very cryogenic fluid to make that tissue dead, the cancerous tissue dead. That also involved the heat transfer in multi-layered or a complex solid, and this transfer of or the flow of blood is equally important. So all common theme in all these systems is complex geometries, and they have some kind of flow around them or in them, and they are also doing heat transfer with the outside system. So any system, if you take, what you actually need is to design them through accurate FSI modeling. That is actually the bottom line to showing all these applications. A little bit more on that. This is similar ideas, but in more detail. So here a piezoelectric fan is used to cool the heat sinks, and what it is showing is different type of coverages could be changing the heat transfer. This is an example of energy harvesting. So these days we have a lot of talk going on about the uses of green energy and how can we go green and things like that. So the available hydrokinetic energy, for example, in rivers or flowing water can be used as a green energy by converting it to electrical energy by some kind of FSI system. There are already some examples and companies have been started based on this principle. For example, Vivas is one company, and there are energy harvesting examples via flexible plates. For example, piezoelectric plates, for example, these ones. I'll talk a little bit more on this piezoelectric plate tomorrow in my last lecture. So these piezoelectric membranes can also be used to take out the flow energy, for example, airflow and wind energy. So FSI modeling could be very helpful to design the system, to understand the dynamics, and to design our experiments. So let us see how we can model these systems, and how can we kind of represent this moving boundary in a flow. So as such, the moving boundary problems in fluid dynamics are anyways harder because the boundary is moving and you have to account for many things. And now with the advent of FSI, there are several challenges. For example, if the body is deforming, body is vibrating, and it is also exchanging heat with the surroundings. So we are talking of multi-phase, multi-physics problems, and we have several physics integrated to it. For example, the structure dynamics, the fluid flow, and the heat transfer. And on the top of that, we have complex 3D geometries and moving boundaries. These boundaries can move, not just be stationary, and large scale structure deformation can occur. That could be due to the high pressure or due to the low flexural rigidity of the structure involved, or very thin structures. And then when we model solid mechanics or structure dynamics, we have to account for geometric and material non-linearity. And when we are writing such solvers, we have to see whether the solver what you're writing is stable, numerically stable or not. So 20 years back, the complex geometry, stationary geometries, block body flows were like standard problems and the state of the art problems. And now these are the problems which is the state of the art. So today, if you are doing block body flows and just doing fluid dynamics, probably you have to be doing some more challenging problems like turbulence and very high Reynolds numbers to be more relevant. So here, if you are doing low Reynolds number problems, so people are talking of more multiphysics problems. For that, you have choice of computational methods. There are two classes of computational methods. One is ALE, arbitrary Lagrangian Eulerian method, and other is immerse boundary method. So the idea of these two methods you can see in this picture. This picture shows that as this plate, which could deform under the fluid flow, deforms and the mesh actually also deforms, and you can see the distortion here in the mesh. And at some point you have to remesh and then continue with your calculations, right? So one feature of ALE method is body conforming mesh and remeshing needed for large deformations. The other class of methods are IB methods or fixed Cartesian methods or fixed grid methods. You can see here the plate deforms and then the grid still remains the same. And here another picture shows these ideas. So this is ALE method where cylinder is just fitted with this finite element grid. Here in IB method, the cylinder is not fitted and there is a background Cartesian grid which is used to solve the fluid flow. So of course, there are pros and cons, and there are several groups who are also working on ALE methods and IB methods as well. Which one is better? Actually, there are pros and cons, as I said. So when we discuss IB methods, we always say, okay, remeshing needed for large deformation. That's why ALE methods are not so good. So you can consider the IB methods, but IB method itself also have several cons, which people who are practicing ALE methods can cite. So if we just understand the advantages and disadvantages of these methods, then I think we are better off. So here in this talk, I'll mostly focus on IB methods, and IB method is also has a wide spectrum of methods, and there is a history of a development of almost 30-40 years of these methods, and there are so many variants of these methods that probably some of you have already practicing it and developing it. So I'll just go to just selective methods, selective IB methods, what has been there. And if you are a beginner, this will definitely help you because this gives you just kind of an idea about IB methods. If you are experienced users, probably you can have a look and try to compare your variant of IB methods versus what I am showing here. So origins are in 1971's thesis of Charles Pushkin, where he wanted to model the fluid flow around a deforming heart. So he modeled the heart in a two-dimensional geometry like a massless elastic fibers. And now once something is moving in the flow, it's actually going to affect the fluid flow. So he basically said that this movement happens, of course, with no slip boundary conditions. And there is a stress which gets generated in the elastic fiber because of the shearing of the fluid flow or the shear stress. And that is also transmitted to the fluid. And these fibers are actually massless. And now these fibers can be represented with another grid or another marker points, which we call as Lagrangian markers. So now we're talking of two grids here, or two kind of mesh. One, of course, is your fixed grid, Cartesian grid. And on the top of that, you have an Lagrangian markers, which are being tracked in a fashion which is governed by the fluid flow. Now to account the motion of this elastic fiber, we need to change something, because if you do not change something, we're going to get the results for the stationary fiber. So if this is moving, we have to add something. Or even if it's not moving, if you want to just record its presence in the fluid on a fixed grid, you have to do something. And what he proposed, that you can add a forcing term in the momentum equation to impose the velocity boundary conditions. Okay, condition here is missing. So this is that forcing term F. So if you think of this forcing term, this units are Newton per meter cube. So you can also call it as a force density. And now, how do we compute and implement that? That remains a question. So now, if you also see other principles here, so the no slip velocity, which is at the fiber or at the solid wall or the immersed boundary, is also following a no slip, which means that the motion of those Lagrangian points, the derivative of that is just the velocity of the fiber, and that can be represented by a function such that we have this velocity of the fluid flow, and I multiply it with a Dirac delta function and then integrate it over the whole surface or the immersed boundary. And now this force, that is forcing term I have added, is basically related to a stress in the fiber, and then there is a Dirac delta function which is integrating over it. Okay. So this is a method he proposed, and of course now the challenge is how do you implement this, and what are the implications of doing this, and what these forcing and these Dirac delta means. That is something I explain in my next slides. Okay, so first, what we understand here, that we have to add a forcing term, a source term in the momentum equation to account for the velocity boundary condition. So this introduction of the source term will help to capture the effect of the presence of the moving body in the fluid. Now let us see what could be the other approach. Other approach is not to add this source term. Now what I just explained you is a primitive or earlier class which was called as continuous forcing, which means that I am going to add a source term in the momentum equation, and then everything is continuous, nothing is discrete, in the sense that I am solving a Navier-Stokes. And in order to account for this source term, I have to regularize this source term, which we will learn in subsequent slides right now. And this will end up in representing a diffuse representation of the immersed boundary, which means the boundary condition may not be satisfied exactly on the interface, and we will learn how. But that's why it is called diffuse. It will be definitely an approximate way to implement the boundary conditions, and of course to remove that limitations, the discrete forcing methods were introduced later. Okay, the discrete forcing methods, the idea also remains similar but not exactly the same. So you have governing equations which you solve as you will solve without accounting for the immersed boundary. So here our immersed boundary is the surface of the solid which you are trying to capture in the fluid, or any surface which you have, and the flow has changed because of that. Now the main thing is what will happen to the flow when this boundary is introduced, and then boundary conditions are there on the surface. So the discretization has to be adjusted near the IB to incorporate those boundary conditions. But this will result in a sharp representation of the immersed boundary that you will have in a typical ALE method. You will have an exact representation of the immersed boundary. So that is something, an advantage of discrete forcing method over continuous. But continuous forcing method is also have its advantages. For example, it is very easy to implement and very cheap as compared to, computationally cheap as compared to discrete forcing method. If you want to see in terms of just pictorial representation, what you are exactly doing is this slide. So you have a immersed boundary or a structure boundary, as you can see here in the red, And then you have a force distribution function, as you can see plotted through blue, right? Think of this as a 3D plot. So you will get to know what this curve means, which means that forcing is very large as exactly on the boundary, but is decays and then becomes almost zero while you are away from the boundary, which means that essentially this green region will get affected. So everywhere in this green region, you apply this force distribution function in order to capture this boundary. That is your continuous or the diffuse method. Here in the sharp interface, you can see this black is representing your structure surface, right? And now you see certain acronyms here, which are actually just the marking of the cells. When you have a solid inside a fluid, I would like to know which cells are of fluid, which cells are of solid. That demarcation I have to do before even I go to implement the boundary conditions. And when I have those demarcations, I can actually apply boundary condition on certain cells. We will discuss again subsequently what are those boundary conditions and how we apply that. But if you apply some boundary conditions on these cells, which are very close to the interface, I think we have a sharp representation in the sense that we are not approximating the boundary conditions on the interface. Now, I'll give you a simple example to see the implementation of these two types of the IB methods so that you can easily implement for other cases also. And the example I choose is for the energy equation or the temperature. Why? Because it is a simple scalar transport and many times it's very easy to understand its implementation. So I'm going to implement IB method with different boundary conditions for diffuse as well as sharp interface. And once you understand this implementation, you can easily extend those ideas to Navier-Stokes as well. So this is the governing equation, continuity, and this is Navier-Stokes, and this is the energy equation. So any system which I explained initially in the first or second slide, all the examples I gave are governed by these in its all generic forms. Of course, depending on the system, you can approximate these equations and you can drop certain terms as well, or you can have more terms. These are the boundary conditions for thermofluids or temperature boundary conditions like Dirichlet, flux or Newman, or mix or convective boundary condition or radiation. And these are the boundary condition for conjugate heat transfer, which means that you have heat transfer going on in solid as well as in fluid. And there are certain boundary conditions you have to implement at the interface, solid liquid interface. So let us see this implementation so you will appreciate how easily we can implement a continuous forcing or a sharp interface IB methods. So there are a lot of equations on slides. We'll go one by one. This is governing equation, of course. And as we discussed from the Paskin's method, we have to add a source term to implement or capture the effect of that interface or immerse boundary. So here in this case, it's Q, right? So previously it was force density. Here it will be, we calling it heat source or sink. And its units are watt per meter cube. Per meter cube is the unit. And now this Q, which is implemented on the whole domain and the whole fluid. Now this one is written in terms of a Dirac delta function, and where Q is defined as a flux on the Lagrangian boundary, as you can see here. So here capital X is the Lagrangian marker point. Small x or the lowercase x is the Eulerian coordinate, and delta is the Dirac delta function. Now I talked of regularization of this source term. So if you think of Dirac delta, it has a value at just x is equal to 0 and then it is 0 everywhere, and that value is actually infinity. So instead of exactly Dirac delta, we used something called discrete Dirac delta function. Right? So, and this is denoted with a subscript small h, delta small h. And now this delta small h we will define in this slide only. But if you see this equation, it has now initial notations ij which is representing your indices of the fluid. And then I have indices K to N. N is the number of Lagrangian marker point. So if I go back to my figure to explain you a bit more, I have Lagrangian points on this boundary or on this boundary, right? And then these any indices of these cell centers are Ij. Okay. So this is the distinction, and K is the kth Lagrangian point, and I have to find out that flux on each of the Lagrangian point, which is given by Q subscript K, and then I'm going to multiply this with this discrete delta function, and this delta Sk is the spacing between the two Lagrangian points. Okay, so the challenge here actually is to find this heat source distribution Q. Once I have it, I actually can solve my governing equation and get the results what I want. So determine the heat source distribution such that it enables the satisfaction of a thermal boundary condition, and it could be a fixed temperature or heat flux on the immersed surface. So one thing to note here, this flux, which I am actually saying flux, it could represent any boundary condition. I have to determine this flux even for a constant wall temperature boundary condition. It is not just, it is valid for just flux boundary condition. It is valid for all kind of thermal boundary condition. Whatever boundary condition is given, I have to determine this flux Q and then Q heat source and sinks. Now, I can approximate the temperature at any Lagrangian point by the same approximation, which is what? Any initial temperature, if I multiply it with the Dirac delta function, discrete Dirac delta function, and multiply by h square. H is my grid size, and that approximates my Lagrangian grid point Tk. Okay, and now there are several forms of this, several types of discrete Dirac delta function has been used. I'm just showing you one example. It is also called as kernel in transferring data between Lagrangian and Eulerian grid points. Now this is given by Paskin. This is also called as 4 delta point function. So the role of this function is to present this smoothing as accurate as you can. So this is actually this function. This is like a kernel which you actually need. Now this is for 2-dimensional setting I am showing, because you can see here it is coming as h square. But if you have 3-dimensional, so you have to go h cube, and then you integrate not over the 2D curve, you integrate over an area. So that's why the units can be balanced. So with these approximations, this temperature, Lagrangian temperature given in Eulerian indices, or this flux, which is Eulerian and given in Lagrangian, we can actually solve and implement this method. So let us see on the next slide how we're going to do it. So first, I'm assuming that you already have a discretization procedure available in your code, and you are using a predictor corrector kind of method and a time marching problem you are solving, and you already have a corrector predictor equation in place, and in the corrector step I'm going to implement my source term. So intermediate temperature field is already there without consideration of thermal boundary condition, okay, which you already probably have in your code. And without Q, I'm going to solve it. I have T star already with me. Now in corrector step, I can actually implement this Q, which I want actually, and then I can obtain the new temperature in the n+1 time step. So you see the discretization here. So I just using a explicit kind of or what we use in a corrected discretization, Tn+1 minus T star by delta T. Delta T is the time step in Qn+1. So notice here it's an implicit representation of our scheme. Okay. Now let us see how we're going to solve this equation. That is the target, to solve this equation. Now I can approximate my Lagrangian marker Tkn+1 at the wall in terms of the initial notation, that the equation I showed. So this equation I have showed you. So I'm just going to apply this equation to the n+1 time. So this is just n+1, and you can see this initial notations I have written. So everybody is probably with me. This is coordinate for the Eulerian grid. This is for the Lagrangian grid. H is the grid size, and this is the Eulerian temperature. I have to sum it up over all indices for the whole domain if I want to find the Lagrangian temperature. And of course, elsewhere away from the boundary, this function ensure that these all are not there. So in a way, you're going to get your Tk n plus 1s affected mostly by the close to the boundary. Now we can substitute Tn plus 1 from this equation to this equation, to the second equation. So let us do that, and we get a huge cumbersome equation. So Tk n plus 1 at wall is given in terms of Tij and with a star, which is the corrector temperature, and then Qij n plus 1. This is something we need to find out. And these are some constants we have. Delta T is the time step. And then again, the discrete Dirac delta function. Now I can substitute Q in terms of capital Q and recall this equation. You are probably with me. So this equation, if you see, I can represent my Eulerian value for the heat sourcing in terms of the Lagrangian heat flux. Okay, this equation I'm going to utilize. And once I utilize this equation right here, I'm going to get an equation. So now let's look at this equation. This is actually our final form of equation, just to solve and let us understand what we have done. So any Lagrangian point temperature at that particular time step which we want to determine can be given in terms of its corrector temperature with a discrete Dirac delta function, and also in terms of the flux on the all Lagrangian points. So when we substitute this, we actually get a sum of extra sigma for all the Lagrangian points. Notice this M is for all the Lagrangian points. And Lagrangian points scales from range from 1 to capital N. And then I get additional terms, which actually all of that I know. What I don't know is this term Qm. But luckily I have the boundary conditions. So I know also this value because I know the temperature at the wall. So let us say I know the temperature at the wall, which is a Dirichlet boundary condition. I know the right and left hand side. This term also I know because I know the corrector time. What I don't know is this. Okay. But now I can solve this Qn plus 1. But this is just one equation. I will have almost like capital N number of equations. Why? Because I have that many Lagrangian points. So actually I can solve a system of linear algebraic equations whose size you can easily determine, and the total points are from 1 to capital N. And once I solve the system equation, I can solve for Qn plus 1. Okay, now Qn plus 1 is given to me known. I can go back and use this equation to find Q, small q. That is my heat source, right? And now once I have this, I can go back to this equation and solve my temperature. So you can easily implement this source term given those Lagrangian points to find out your new temperature field. This is the implementation of continuous IB method. Now, of course, you can argue, okay, what if I given a different boundary conditions? So other boundary conditions are also very easy to implement. Now let us talk of the flux boundary condition. For the flux, you can define an additional virtual layer of points which are equal to our total Lagrangian points, which is away from grid spacing H outside the boundary conditions. Let us call it VB. Why call VB virtual boundary? Because it is anyway not there. This is for our computational tractability that we define and use this. And it's also aligned in a direction normal to IB because we are using a flux boundary condition. Now I can approximate my flux at the wall as Tk at any Lagrangian point at VB virtual boundary minus Tk wall, okay, and divide by H because I have taken these points at away from H. Now if I rearrange the term here, I get Tk any Lagrangian point at n plus 1 at time at wall in terms of the flux and Tk n plus 1 VB. Now Tk n plus 1 VB you can determine using interpolation, and that interpolation is something we are using already. So this one VB can be determined using this equation. So this way I actually again get a slightly different form from this equation for the flux boundary conditions, and you can also implement the flux boundary condition. With these two basic boundary conditions, you can also implement the mixed type boundary condition. You can also implement any radiative boundary conditions. So with this framework, you can implement easily the continuous IB method. Okay, so with this, of course, you may have several questions regarding grid size and what if we refine and how the accuracy change, and that's something that we can also discuss once we have completed the presentation. But the bottom line is the continuous forcing method is easy to implement if you are given a geometry and you approximate it, approximate the effect of it using a source term in your governing equation. So with this, let me move to the discrete forcing method. In that we have a different approach, and this is our boundaries, solid liquid interface. What we need to do first is identify different kind of cells. So these cells are called as solid, fluid, and Bose cells. Okay. Now we can see here, I am putting different kind of dots here. This is for fluid, this is for Bose, this one for Bose, and the solid cells. So of course, cells which are in solid, they are solid. Cells which are in fluid, they are fluid. But what are the Bose cells? The Bose cells are those cells which are in the solid but have a closest neighbor to a solid cell. So every Bose cell is a closest neighbor to the solid cell. This is the definition of Bose cells, and we will call them Bose cells. I'll tell you later why. Okay, now once these Bose cells are defined, I will take a Bose cell and draw a normal to my boundary, and wherever it will intersect, I will call it BI. BI is for boundary intercept. Now I'll continue this normal and go in the fluid and reach to a point where the distance between BI to Bose cell is equal to the distance between BI and IP. And I will call it as image point. Okay, IP is for image point, GC for Bose cell, BI for boundary intercept. Now this framework is required to apply the boundary condition. We will see how. So the idea of this applying this type of boundary condition in sharp interface IB method is somewhere in the potential flows. If you are doing potential flows, and if you have heard of something called method of images, then you will know what I'm talking about. So something Ghost cell, a cell on which we will calculate a velocity, but it is an inside a solid, the velocity is not there, and that's the reason what we call it as a ghost cell. Okay, and there is a velocity, of course, defined on this BI because it's the interface, and that is image point. So image point is the image of the ghost cell. Okay, let us see with this framework how we can define the boundary condition in the sharp interface boundary method. So first we assume that temperature in a cell can be approximated using a trilinear interpolation, which means that the temperature at a given point or a given cell, I would say, is a function of some constant and the locations. So let us say I have this temperature, which is a function of the locations and some C's. So any given cell which is surrounded, which has actually the IP. So once we have the IP, we found a surrounded cell. And those cells are like the neighbor cells for IP. So any IP which we have found in our fluid domain, we will look for the cells which are closest and surround this IP. And they will be 8 in number, because you can think of a cuboid where you have a point inside and you can see there are 8 nodes around it. So there are around 8 cell centers on which I know the value, in the sense that because it's in the fluid. So this Eulerian grid method, we know the values, because you remember first we solve the boundary, the governing equation, and then we apply the boundary conditions. So this is just, we are applying the boundary conditions. So how we will do it? First, using these 8 cells, I can apply this equation. So let us say I have first cell T1 and I know its location. Right? So I actually can find out all these constants, C1, C2, C3, C4, C5, C6 using AX is equal to B system. And once we use AX is equal to B system, we will get something called van der Monde matrix, and this is represented here as V. So if we take the inverse of V, so this matrix is just the function of the locations, and this Ti is the nodes 1 to 8 adjacent cell centers around IP. So I have the information of Ci, all the constant. Now if we substitute this second equation, this one what we have obtained in first, which means this first, to find the temperature of the image point, that is our target. If you find the image point here, TIP, the temperature of the image point, we can find the temperature of the ghost cells, that is the target. So we substitute this equation in this generic equation to find the temperature of image point. And we can write it in this form. You can see the summation from I is equal to 1 to 8, BI's. So BI's is just a function of Ci and location, which we obtained by substituting this in there. And this can be used to find the image point. Here, of course, right now betas are unknown, but we can figure out what they are. Now, Dirichlet boundary condition is given by simply TBI is equal to half TIP plus TGC. Okay, so this is by definition, because if you see, if you think of that this temperature here and this temperature here, so TBI is the sum of these two. So this is the way we define the boundary condition in the sharp interface, right? Now, if we have the boundary condition here, we can use the TIP expression, which we have figured out from previous slide, and you can put it here. Now we have everything here in the sense that TBI is known, right? And BI is the function of your locations, and then TI is your 8 temperatures. So you can actually solve this equation in a coupled way, in a coupled manner with the governing equation. Once you solve this coupled equation in coupled manner, you can obtain TGC. And that you have to do for several GCs, not just one GC. All GCs you have to do. So this equation for all GCs will result in a solving like AX is equal to B system. This is something very similar we have done in continuous IB method when we solve for all Lagrangian points, right? And once we solve TGC, you can substitute this here, and TIPs are known, so you can figure out. So TBI is given, so you can figure out TIP. So in a way, you can figure out all the temperature field using this approach. Now, how to apply the flux boundary conditions in this framework? So the flux can be easily written as TIP minus TGC divided by delta L. So this is using the central difference scheme, which is second order accurate. Now, if you go back here, if you see, I am just having 2 steps here. So I am just taking this whole TIP minus TGC, that is my flux. And now this equation results in this equation, which is TGC is a function of, again, image points, and then, the adjacent nodes to the image points and all the flux, and which is actually known. And this again can be solved in a coupled manner with the governing equation to figure out all the temperature field. One thing you can quickly notice that we have used a central difference method for the sharp interface. And when we applied the flux boundary condition for the continuous IB, we used first order discretization, which was not second order, first order accurate. So here you can see the accuracy actually improves very close to the interface if you are using the flux boundary condition. So that way the sharp interface method is better, but of course it requires more framework and identifying the cells. So computational infrastructure required is more than the continuous method. On the other hand, continuous method is easy to implement and also computationally inexpensive. Now, one last thing I would like to say, conjugate heat transfer boundary condition, how would you implement? And that is something extension of the previous framework, and we can understand here very easily. So we have understood how to apply the flux and the Dirichlet boundary condition in the previous slide, and that is something using the ghost cells and the image point. So ghost cells in the solid and the IP is in the fluid. Now, if you have a conjugate heat transfer, you are solving also the heat transfer in the solid as well. So you have to define something called mirror ghost cells and mirror IP. So you can see this figure where you identify all these cells, IP in the solid and IP in the fluid as well. So first you do as you do for solid and fluid, and then you go back and do again for the solid as well. So here is the formulation. This is something we have done before, but we just put the stars. So stars are for the solid domain. And once you have this equation, we can apply these two boundary conditions easily. So these are the flux boundary condition at the interface, and this is the temperature. And if you just do some reworking here, you can get a single equation which will ensure that your conjugate heat transfer boundary condition be applied easily. Okay, so this is just how to tackle the structure boundary equation in the fluid. Now, let us say you want to solve for the structure dynamics itself, and you not only you have structure dynamics, but also you have fluid dynamics. So you have two kind of systems have to be solved together. Of course, it's much easier if you just make a single governing equation, which is actually called as monolithic approach, and then you just write a solver from the scratch that you're going to account for both together, and that something has been done by several groups as well. But what is more common is the partition approach, because a fluid mechanician started to integrate a structure dynamics in the code available to them. And that is something called as partition approach, where you have a fluid solver already, and structure solver is something you get it from somewhere, or it's open source code, or you write a small structure code, yeah, and then you solve it in an iterative fashion. So partition approach uses existing fluid and structure solvers. I mean, of course, you can write the structure, but it's more common is you both, and then it is having large computational time as compared to monolithic, because of course you're going to iterate back and forth between the fluid and the structure solver. And then once you are having two solvers, you are talking of stability issues, especially when things are moving faster and in large magnitude. Okay, so partition approach works like this. You have a fluid, you have a solid, and you go back and forth to exchange the data. And this data is actually the boundary condition, kinematic and dynamic boundary conditions. So the match is of the solid displacement and surface velocity in the flow solver and the structure solver. And the second match is the fluid dynamic forces on the structure, okay, which will help in generating the stresses in the solid. So these two conditions simultaneously should be satisfied while you are announcing a convergence to your solution. Okay, so so fluid computation can be done on Polarian grid if you are using an IB method, and then immersed surfaces which you can track in Lagrangian framework as we were doing before in either continuous framework or either a sharp interface. And then you may have another solver, structure solver, which may be using some scheme. Let us say finite element method it is using, and that solver also has to be coupled. So that finite element solver need to see also those Lagrangian point, and then the Eulerian grid also need to see those the Lagrangian points. So probably you get the idea. You need to solve boundary condition on two solvers, and they have to be satisfied together. Now let us see how we can achieve the numerical stability of such situations. So let us say I already have a plate which is deforming, and the solution is obtained at nth time step, and I'm looking for the solution at n+1 time step. And also I have the deformation available. I'm calling it with a big gamma. And this is just my first time I'm going to iterate. Now what I need is the solution at n+1, which include all the velocity and pressure field, and also the interface position. And of course, I'm going to need also the stresses inside the solid and things like that. Now I call the fluid solver and solve a time marching problem, as I have done probably in regular cases before. So that gave me n+1 data for the pressure field and the velocity field. And now this will have a certain force which is applied on this solid, and then you will have certain deformation. And that deformation, of course, is this. Now, that deformation is here in this particular step. Now, the question is whether this deformation is going to satisfy the boundary condition, in the sense that when you have matched this fluid flow from this to this, you may have a certain field, but that may not be exactly satisfying the boundary conditions. For that, you have to check and go back to the fluid solver and check whether essentially it is true. So we can use an under-relaxing parameter, and we can under-relax any variable of your choice, let us say interface velocity, interface position, and then you under-relax, and then again and check, go back to the fluid solver to see whether my solution has been converging or not converging. Okay, so let me put this thing, if it is looking complex, in an algorithmic form. So here it is. So first you solve for the flow and pressure field, then you solve for fluid dynamic forces, right? And then you solve for the deformation and stresses, and then you actually get a new interface position and the velocity. There are maybe more values for everything, but these are the things I am more concerned with, because these are the things going to talk to the fluid flow or the fluid solver. Okay. Now I calculate the residue between my old and new. So remember, this is not the old time step. This is the old iteration. So I am having a global time marching for my fluid solver if I'm integrating a structure in it. But then also I am sub-iterating within that step with the structure solver. So this is the old of my sub-iterations, which I have designed for the converging solid and fluid together. So I announced two residuals. One is based on interface position and other is based on interface velocity, and I can check which residual is larger. And then if it is not converging, I can go back, under relax, and then I feed this old value, new values here, which I have obtained here, to the old ones, and again go back. And I keep checking until my residual goes almost to 0. Okay. And now a little bit next level to it is use the under relaxation as a dynamic one, which means a faster convergence. So this is called as Atkins method, where it allows you to choose these residuals as based on as your solution is going. So it's more a dynamic under relaxation scheme, which will converge your solution faster. Okay, so that is something you can also implement to make your codes faster. This is called as Atkins method. Now let us see what kind of results we're going to get from such kind of schemes. So this is results. We have used an implicit partition IV method, a sharp interface. And this method originally was developed in Professor Rajat Mittal's group at Johns Hopkins. And since then, we have developed it extensively for many things, including thermofluids and many other viscoelastic structures and many more things. So the structure solver we are using from open source. It was developed in Sanjay National Lab. It is based on finite element method, and this is a typical surface grid we are showing for our code. This is a cylinder attached with a 3D plate, and the flow solver is a second order accurate. As you can see, it uses Bose cell methodology and all the second order schemes. So now, if we use this famous problem of Turek and Heron FSI benchmark, and which has been simulated by several groups. Here the cylinder is stationary and there is an elastic plate which can deform under the vortex shedding forces or under the pressure forces, and it actually sustains those vibrations because it locks to the fluid frequency. And then this is a low Reynolds number problem, and the density ratio also here matters, which is around 10, and the Young modulus non-dimensional is 1.4E3, and we are using a linear elastic model. So this is something we'll discuss. Here in this model, we take the geometric non-linearity into account, which means that if you are having a large deformation, we take those effects into account. but the structure material itself is elastic. That is the meaning of this linear elastic model. And this is the vortex shedding. I think I'll just show you the movie. You can see that how the plate starts to deform, and then it attains a self-sustained vibration, and then there is a vortex shedding in the downstream. Now, if we plot the evolution of the tip of the plate, it looks something like this. This is the Y displacement, which attains again a self-sustained state, and this is the X displacement, which is slightly smaller than the Y tip. So we can compare Y tip that has been benchmarked in several studies. Here we have benchmarked it really well. It agrees well with the earlier data. And now we also test the performance of our under relaxation. Now you can see here in this problem, we have choose certain times to plot the convergence. So this is red is without any dynamic under relaxation, the constant value. But these two other curves, blue and black, are showing dynamic under relaxation. So there is slight difference in the sense that we set a limits on the under relaxation parameters, whether it is small or whether it's the smallest possible is 0.1 here and the largest is 0.4. There's slight difference there, but the bottom line is it gives a good improvement in the computational time on the order of 50% to reduce the computational time. We have done other problems also. For example, a thin plate is attached on a square cylinder, and you can see the mesh here in the plate. So we refine it quite a bit to make sure that we capture accurately the motion of the plate. And that problem uses a slightly larger Reynolds number and larger density ratio. This is also a linear elastic model. So our solution agrees well with the published results. Then another problems we validated is vortex induced vibration. There is a cylinder mounted on a spring and it undergoes vibration. And probably I think in the workshop, Professor Mittal has already talked of lock-in. And so some of you already familiar with these this physical phenomenon. So the cylinder goes to vibration, and what we compare is the maximum amplitude of this signal or the maximum displacement. And this is plotted with respect to the reduced velocity, and we are comparing well with the other studies. Now we have also validated in presence of thermal buoyancy. So in code we have implemented thermal buoyancy with a Buzinac approximation, which means the linear variation of density, and that too only with the temperature gradient. And here we've compared with earlier results and agrees very well. In the context of biolocomotion, we have validated our code for a moving or a flapping rigid ellipse. So these are the motions of this ellipse in the two cycles, and forward and backward. And this is the published result, and this is our results. And the comparison captures all the mostly all the peaks in the lift and drag signal. And as intended, you can see there is a lift generation in this FSI system, which is showing a positive lift. We have also done simple exercise of heat transfer, like conjugate heat transfer, where there is a solid body which is exchanging heat with the fluid, and also earlier tests like natural and mixed convection, where a cylinder is placed in a fluid, and what is the variation of the Nusselt number on its wall. And this is actually a cavity with a natural convection. This is a flow over a cylinder with mixed convection. So other tests such as coupled conjugate heat transfer and natural convection also we convincingly obtained. And we also did a problem with conjugate heat transfer and large scale deformation that I haven't put, but that is also possible with our method. Now let me talk a little bit more physics. Yes. Can anybody update me how much time I have?
Sir, it's 5 to 10 minutes.
Okay, I try to finish in 10 minutes.
Yes.
And whatever I could not present today, I can present in integrate in tomorrow's lecture. So now I'm going to talk apart from the numerical methodology, some of the application in thermofluids, and also talk a little bit of physics in these systems, in this FSI system. So we integrated a thermofluid problem in FSI, and the same Turek and Heron problem, when what I was showing, we solved the temperature field in that. Here we are using the heated boundaries and using the insulated boundary of the cylinder and the plate. So the idea is to see whether this motion of the plate can improve the heat transfer or not. So here is the movie which I want to play here. So you can see that the cylinder is attached with that elastic plate, and the plate is attaining the self-sustained oscillation, and downstream is really long in order to capture that thermofluidic behavior. So the third column is the row is the vorticity, and what the fourth is the plot of Nusselt number on the walls. So whenever a signal is going up, which means that Nusselt number is going larger, which actually we want. We want a larger Nusselt number for the improvement of the heat transfer. And what this part is showing is the isotherms. Basically, this red color here is actually thermal boundary layer. And the idea is simple here. So the vortices which are generating from the tip of the plate, they are hitting the wall and they are thinning down the boundary layer. So if you have done any course on convective heat transfer, probably you know that thermal boundary layer is the kind of resistance to the improvement of the heat transfer. All you want to do just kind of disrupt that thermal boundary layer to improve the heat transfer. And that is exactly the system is doing. Just these vortices interacting with thermal boundary layer, thinning it down and improving the heat transfer, as you can see here. And by its very design, you can see the signals are out of phase, and sometimes there is always a phase difference. Why? Because the vortices are hitting at different times. When you are having a top wall, then these vortices go back to the bottom wall, so on and so forth, right? And then of course you can see a infinite value at very entry of the channel, because the thermal boundary layer thickness is 0 there. So that shows we have a certain improvement by just looking at the peaks of this Nusselt number. But whether it is good enough is something we kind of test in the next slides. So for that, we just compare this system with 4 basic systems, 3 basic systems, and the 4th actually is the actual system. So one is the pure channel, nothing is there, and the second is the cylinder. As you can see here, it generates these vortices. So I'm plotting the vorticity and isotherms in these systems as well. And the third case is a plate, but that is very rigid. It cannot deform. Stiffness is very high. So here also you can see the shear layers, which are not able to create the vortex shedding. And here you can see the isotherms. Here the 4th case, which we were discussing, which is a passive kind of way to improve the heat transfer. And you can see the thinning down of the boundary layers and things like that. So this is looking at least giving a qualitative information. To be quantitative, we plot the Nusselt number, and that Nusselt number is time average, because it's a cyclic process. I mean, the vortex shedding itself is harmonic. So we time average in all cases, and with respect to space we are plotting. This is the downstream. So you can see the black signal, which is just pure channel, and that should match with the analytical results what you have learned in your convective heat transfer course. And now once you put the cylinder, the red one, you see some vortices which are also helping to improve the heat transfer. This is a red signal, but it's still not good enough. The third is the rigid plate and with a cylinder. That case is the worst, because that also does not have any vortex shedding, and even it is sometimes lesser than the channel itself. And now the 4th case, which is our present case, And you can see these two big peaks is actually helping to improve the heat transfer, and that peak significantly showing in the downstream. The vortices are being hit at these locations. So not only it improves the heat transfer, but also this analysis tells us like where it will improve a lot. So if you have some kind of non-uniform heating or non-uniform load to be removed, that method can be used. Another thing about this method, it's a passive method. There are no active motors or anything involved. So passive cooling is desired and preferred if you see the heat transfer literature. And now how do we assess its efficiency, how much it is efficient? Because when you do that, you also create a pressure drop in the channel. It is coming at a cost. Now, for that, we actually define an efficiency, which is simply eta h by eta f. Eta h is the mean Nusselt number, both time and space. Now I'm also averaging over the space, both time and space, and this is nu mean divided by nu for channel. So I'm just basing everything for on the channel. And this is P average, which means how much power I have to use to derive this flow. So P average divided by P average for channel. So if you divide this ratio, basically accounts for both things, the pressure drop, and also it based my efficiency on the channel, how much I'm able to improve with respect to channel. So look at the Nusselt number first. So these are different simulations have been done. We have varied the Reynolds number. We also have varied the Prandtl, and we also have varied the non-dimensional modulus of elasticity. So clearly, if you just see one case where CHL is for channel and cylinder, and this is for rigid plate and deformable plate, the deformable plate is huge, as you can see here, right? And now if you see as compared to these two cases, which is CHL and CRP, it is also efficient. As you see in this plot, you can see the efficiency is larger, and simply just using these two cases, cylinder or rigid plate, I would rather use this deformable plate because it's giving me a larger efficiency as compared to the other two. And you can see that the power is large in the deformable case because the plate vibrates to a larger extent, and of course it increases the blockage ratio. So the power spent is more. But on the other hand, I also get more improvement, and overall this process is more efficient. Now, if you increase the Prandtl number, we see slight change in the efficiency values, as you can see here. But if we increase the Reynolds number, the improvement is large, but the efficiency goes down. As you can see, this process is not so efficient as compared to the Reynolds number of 100. Now, in the last case, yeah, the 2.8 has very low deformations, and that's why the efficiency and the Nusselt numbers are lower. So we can understand these results in the context of the pressure drop and efficiency. So maybe in the interest of time and would like to listen from the audience, I would stop here, and I have some slides left, but I would like to integrate in tomorrow's lecture. So probably it is fine right now if we can take questions.